So in Gen Chem and in chemistry in general, we deal with solutions all the time. So hopefully throughout this far through, you've kind of gotten used to the usage of a solution. Now, typically we're going to keep our Gen Chem course to be primarily aqueous solutions, to be in water. But just know that there could be solutions of other sorts, and I'm going to have a couple of them come up this time. You could have an organic solvent solution. You could even call a gas phase a solution, or a solid phase. You could have a solution like a metal alloy is often thought of as a solid phase solution system. And it just means that you have a solute, one thing, dissolved in another thing, the solvent, to make the overall solution. We'll return to this again in class, and I just wanted to mention it here. I think we probably do need more practice. I'm getting rid of the delta T here, the little t for time. And I want us to stay in energy units, joules. Use whatever energy, calorie, whatever, but energy units down here instead of time. I think that's going to make it more confusing if we try to go to the time thing. So just know that our y-axis is going to be temperature, and our x-axis is going to be energy added to the system. Now, one of the things that somebody talked to me about, one of the students talked to me about explaining to make sure this is clear, is A to B section. So for a typical, let's say we have solid, liquid, gas heating curve here. This A to B section is going to be your solid heating up. B to C is going to be your solid melting. C to D then is going to be your liquid heating up. D to E is your liquid boiling. And E to F is heating up your gas phase even further. Now, that's just a typical where we have a solid, a liquid, and a gas. That's not the only way to arrange one of these, but we'll keep it simple for examples and stuff like that in this course. But know that this could be any sorts of phase transitions. When you have polymers, when you have glass transitions, the same things will apply. Although sometimes the delta H's will be different directions. So unfortunately, this is going to make this recording a little longer. If you don't need this review, skip ahead a bit. But I think that a lot of folks will appreciate a review of some of the calculations and some of the terminology dealing with solution concentrations. By way far, the most common solution concentration that we're going to use is going to be molarity. The capital M, which is defined as moles per liter. Please be extremely familiar with this. This is moles of solute per liter of solution. And that's going to be important a little bit in contrast to some of these others. Section 3.3 in your textbook. Make sure that you can follow molarity especially. It's the most important. The others are also important, but molarity is going to be over and over again. You're going to see it in lab over and over again as well. Your book points out the idea that there's a limitation here that it is temperature dependent. It's technically true, but even graduate level chemistry have never once had to correct molarity for temperature dependence. So I think this is an extreme case. I still haven't talked to any chem engineers about this and what they think. I need to update this slide when I do. Okay, now this is different, molality. And instead of the capital M, it's going to be a lowercase m. It's an unfortunate usage, but it is what it is. It is defined, now this is different. So remember that molarity was moles of solute per liter of solution. In contrast, molality is moles of solute still, but per kilogram instead of per liter, and instead of solution, it is per kilogram of solvent. Not weighing the overall solution, only weighing the solvent this time. So usually numerically there's not a whole lot of difference until you get to very concentrated solutions, and then it's drastically different. So read up on that guy. We're going to definitely use him in a lab, and it does come up in a few cases through chemistry. Just know that it's the molality instead of the molarity. And since the molality is all about mass and moles, well, none of that is temperature dependent. So one advantage to molality is that it is totally temperature independent. I don't want to spend much time on this. Normality, it's actually, I don't think, is commonly used anymore. Most folks use molarity. One of the big exceptions is acids. A lot of times acids are still labeled with normality. For a single charge system, it's exactly the same as molarity, but for a double charge system, it's 2 times the molarity. I'm not sure what the history of this usage is. I know that back when I was taking Gen Chem, this was a big deal. Everybody was trying to drum normality into us all the time and contrast it with the other solution units. But honestly, I don't see it being used all that much more. One big thing I want to say is if you're going to be working in a lab, you should definitely know that it exists and be able to go back and translate to it when you need to. But it is basically charge equivalence instead of, so for the 1 pluses and 1 minus, it's exactly the same as polarity. But with 2 plus, it isn't. So another way to get out of temperature dependence, and this one is actually used more in gas phase reactions than it is in aqueous, but it is a thing. It's mole fraction. So you're talking about the moles of one solute A versus the total moles of all of the solution components added together. So basically, it's the percentage of the moles, it's a molar fraction, that is A. So we used it a lot in geology, but that's because our temperatures there were drastically different, and like water is not a solvent there, it's often a contaminant. So do be able to use all these different concentration units, but molarity is our most important. And of course we are going to use molality in the lab for the temperature depression lab. So I'm going to start to use an abbreviation here, IMF, sometimes for intermolecular forces that we've talked about now. So forces between one molecule and another. So IMFs for solution, or we're talking about solvation energies. So let's look at a scenario here. We've got a sodium ion and a chloride ion, right? So you've got a positive and a negative, and they're attracted to each other by this ion-ion interaction. That is our intermolecular force here. So there's some energy in this, and I'm using air quotes here, bond, at least this ionic interaction, this electromagnetic interaction that is holding these atomic centers in relative stability spatially for each other. So we call that an ionic bond, for lack of a better term here. So that's an energy and interaction, a force, let's say. And force might be better to picture it, but it's really an energy more than it is a force. But it is holding these guys in proximity to each other. Okay, I think, let's see. Okay, these are my solvent molecules. Now what I've got here, since we're talking mostly aqueous solutions, these are water molecules. Right now I've got the little partial symbol here. So there's a partial negative end on the water. There's a partial positive end over on the hydrogen end of the water. So this is a dipole system. And this negative end will see these positives and these positives, and they'll all try to hold together, right? So there's a dipole-dipole interaction between all of these, right? Okay, so now what's going to happen? That's our solvent. So this up here was our solute-to-solute interaction. Now we have our solvent-to-solvent interaction. We need to compare the idea of the solute versus the solvent interaction. So what we can do is we can think about that positively charged sodium. It's So we got this big chunk of positive charge here on the sodium ion, right? But look at this. Each of these waters has a negative, a partially negative. It's not a full -1 in, but it's a partial negative on each of these different oxygens. So what can happen is they can start to see that positive charge on that sodium and all kind of cluster around it like that. And you get this, it's three-dimensional. I've drawn it two-dimensionally here, but it's really all the way around 3 dimensions. You get this shell, like a hydration shell of water molecules locked in around, really tight around your sodium. Now, it can get more complicated than that too, because you've got all the negatives pointing in. Well, that means you've got all the positives pointing out. Well, more waters are going to see those and make another second hydration sphere. You can make a third and a fifth or whatever, each time weaker and weaker exponentially out because of the square cube law. But you do get this interaction now between the solute. Here I've got it drawn as the sodium, but similar would happen with chloride. The water molecules would just be flipped over so that the positives are interacting with the chloride. Back in chapter 5, there was a neat example of a cold pack and how you get the heat of solvation. And it just kind of snuck in chapter 5 where we were really talking about enthalpy. Now might be a good time to go back and review chapter 5 to make sure that you're solid on the enthalpy, the internal energy held in bonds. Now here we're going to add intermolecular forces now that we've gotten deeper into the chemistry, we can talk about intermolecular forces, and we're going to include those in our bond energies, even though they're intermolecular bonds. Okay, so looking at those types of interactions that we had before, we're going to break each of those down now. We're going to talk about where we have to put energy in, right? Okay, so look at it on a molecular scale. So we have the delta H here. So obviously we're going to have to put energy in to get this solvent to let go, right? So this is going to be an endothermic step here because these guys are trying to hold together and we're ripping them apart like this. That requires an energy input. Similarly, here's our solute, like our sodium chloride. Now it's being held together. We're going to have to rip it apart. That's going to require an energy. But here's the thing. We talked about now there's also this solvent-solute interaction. And so we get back some energy out of that one where they come together and start a solute-solvent interaction. Okay, so we could have a situation there. And so we get an overall, we call this a heat of solution, right? And so if our product here has less energy in it than the sum of our reactants, right? And products minus reactants would be overall a negative value, right? And so if there's less energy held in our final product, some of the energy had to come out, it had to go somewhere because you can't create or destroy it. And so that would be an exothermic process. Or the reverse, if there's less energy in this, if there's more energy on, the reverse would be there's more energy of this product than there are in the reactants, some of the reactants, right? Then that would be an endothermic process, trying to get it to go into solution. And so if you have a situation where the sum of the delta H's of these two steps where we break these apart, if this is less than the delta H of going into the solute-solvent interaction, right? So if you look at that versus this one that's reversed, right? So products minus reactants, right? So if this is greater than minus this is going to be a positive value, right? So that's an endothermic. And so similarly, you could have an exothermic system. Okay, but now there's actually a fairly easy way that we tend to look at this. This is the most used version of what all we've been talking about, and it's usually summed up by this: like dissolves like. So you want to use a solvent that has similar intermolecular forces to what you're trying to dissolve, right? So if you want to dissolve nonpolar molecules, right, because of the interactions, you want to use nonpolar solvents to do that. So if you want to dissolve an oil, use another nonpolar solvent like a hexane or something like, or benzene, something like that. Those are nonpolar, and they will dissolve other nonpolar molecules very well. So, like carbon tetrachloride is a nonpolar molecule, right? Even though those are polar bonds, they balance out perfectly. Well, but you know what? It dissolves really, really well in benzene because both of those solute and the solvent are nonpolar. Similarly, if you want to do polar molecules, it's better to use polar solvents. For instance, this is ethanol. Ethanol dissolves perfectly well in water. So you can dissolve any fraction of ethanol in water that you want to, up to and including when you're now getting so far along that you're dissolving some water in your ethanol. And just to point out that ionic compounds go along with the polar because you get that positive negative interaction. So ionic compounds like our sodium chloride, you know how you can dissolve salt in water because water is polar. But if you try to dissolve salt in this benzene up here that's nonpolar, it actually does not dissolve much at all. I want to touch briefly on the idea of electrolytes. One of the things I'm doing here is previewing our acids chapter coming up later. So electrolytes are things that will dissolve, and because they produce ions, they give a solvent the ability to conduct electricity. Non-electrolytes won't do so. So strong electrolytes, and then here we're going to use this strong term, and I'm about to use weak in a moment. But strong electrolytes, essentially all of the material, 100%, is going to generate ions. It's going to dissolve in solution to generate ions. But you could also have an idea of a weak electrolyte, so that a little bit of it breaks up and creates ions in your solution. So as an example, if you put in your water, if you put something that's let's start here in the middle with a strong electrolyte like sodium chloride or even HCl, hydrochloric acid, makes a very strong electrolyte because all of that breaks down and provides ions, H pluses and Cl minuses. So those are all available to conduct electricity. So that'll conduct very, very well. Contrast a weak electrolyte, let's say vinegar, which is acetic acid. It's a rather weak electrolyte. It'll break up and it'll give you some H pluses and it'll give you some acetate anions. They're there. They'll conduct electricity. See how the light bulb is dimmer here? They'll conduct, just not as well. So they're weak electrolytes. Or you can drop something like, let's say, iron oxide. Now, iron oxide is a non-electrolyte because you drop it in your water and essentially none of it dissolves. So if you check this water, you've got a chunk of iron oxide lying on the bottom, and essentially none of it is ions conducting electricity. So for anything charged, and that can be dipoles or it can be fully charged species like cations and anions, the water molecules are going to interact with, there's an ion-dipole interaction. Those water molecules are going to surround it, we call it solvate, those different ions, that's those shells of water that I was talking about forming around your ion. And we're gonna call the process of dissolving, we call it dissociation of those ions. And here's kind of a graphic of what's going on. So So you've got the potassium here in the chloride, right? This is our nice KCl crystal. And here we've got a water molecule starting to interact with. These are interacting with it more. These guys have gotten one of them pulled off. Here you've got that hydration sphere starting to form. Here's one starting to form around the chlorides. So eventually all of these will dissolve away if there's enough of the water molecules about to interact with them all. Okay, and so then we're going to talk about what happens with these solutions when they start to do this, when they start to dissolve these solutes in them. They have what's called colligative properties. So colligative properties change the properties of the solution, and they care about how much solute is dissolved in them. Now, one of the cool things that we can do a lot of science with is they only care how much, not what it is. So we can use that to do some special tricks in the way we're trying to do things. We're going to use it in one of the labs when we talk about freezing point depression. And we'll talk about it. So you can do various different things with it. So we can do vapor pressure can be decreased by solutes dissolved in your gas or in your liquid. You can have a boiling point elevation so that it's harder to boil things. It's harder to boil salt water than it is pure water. But similarly, it's also harder to freeze your salt water or something with a lot of dissolved solute in it. And it's interesting that the boiling point goes up, the freezing point goes down. I think that's an interesting interaction, and I don't have a clear answer for you as to the why on that. It'd be interesting to talk through what you speculate might be the reasons for that. You can also have a change in osmotic pressure. Biologists, y'all know how osmotic pressure changes the cells, the pressure inside, and what's dissolved in your solution changes how it interacts with the bilayer. So I mentioned vapor pressure there, so I want to think back to chapter 10 and what our liquid vapor equilibrium looked like. So you get this equilibrium. I wanted to circle that because I wanted to point out that equilibrium arrow. Just make sure that's not confusing to you. It just means that the liquid is becoming gas while the gas is becoming liquid, and we reach some equilibrium balance between liquid and gas here. Both are happening back and forth. So once we reach that equilibrium, right, then you get the vapor pressure of a liquid. So you can measure the pressure above. So think about one of the typical examples of this is there's a vapor pressure above, let's say, an acid container, right? And so what that's doing is if you were to solidly cap let's say a 12 molar HCl solution, right? Well, that's going to develop pressure in, let's say, the gas phase above the liquid solution. There will be a certain amount of HCl molecules in the gas phase, and they exert a pressure, a gas pressure, just like we talked about the gas laws, that kind of pressure, just by pushing up out of the solution. Because remember, it's always an equilibrium. Some of them are going to gas and some of them are going to liquid because of that Boltzmann distribution. One way that I have seen vapor pressure lowering described is this complex looking diagram over here. So what we're basically saying is we're taking a non-volatile solute, right, and we're putting it in a system such that it lowers what would be the vapor pressure by mixing in, and you get this depression curve that is somewhere between the two extreme endpoints along that. So you get Raoult's law is this, and so the delta P is how much your property is decreasing the measured vapor pressure. So you're going to measure the vapor pressure with 0 solvent, and then you're going to start to add the solvent, and we're going to look at the change in the vapor pressure based on the amount of solute that you have in there. And this shows one of those usages of, in this case, one of the other concentration units, in this case, mole fraction. It turns out that you can go anywhere along that line by saying the mole fraction times the pressure gives you the pressure of the overall solution. So the pressure of the solvent times the mole fraction gives you this. And that gives you where you are along that line on the last slide. So why does that vapor pressure lowering occur? So we've got this equilibrium set up between our liquid and our gas, right? We know that the molecules are going back and forth both ways, right? So what we're saying in equilibrium is that the rate of condensation, gas to liquid, remains the same because like the gas, there's nothing bothering the gas phase. Let's see if we can get the images here. So you have solute molecules in the solution. They are interfering with the surface of the liquid. They're keeping stuff from going from the liquid phase, this top arrow, to the gas phase because they're occupying some of the space where that interface is taking place. But the gas one is not having that problem because as soon as it hits the surface, even if it's one of those other solute molecules, that's fine. It's becoming part of the liquid phase. So the surface area available for the liquid to gas is being impacted, where the surface area available for the gas to liquid is not being impacted. And so the rate of liquid to gas goes down while the rate of gas to liquid does not go down. And so you get this vapor pressure lowering out of that. And here's a graphic that might show it a little better, right? So here we have pure water. So we've got some going from the liquid down in the bottom up into the gas phase, right? We've also got some coming down out of the gas phase into the liquid phase, right? And they're balancing each other out nicely. But here, now we've got these big purple ions sitting in there causing problems, right? And so still we've got some water molecules getting out and some trying to get back in, but your overall number of molecules getting out is decreased. So you have this interaction problem here at the surface, and it causes a lower pressure. Okay, so boiling point, elevation, freezing point, depression. So of course, we're going to math these things. We're going to play with them in experiments. So a solution boils at a higher temperature solution does than what it would be if it were pure solvent with no solute in it. So we're going to call the difference in the boiling point the delta T of B, delta T sub B. And then similarly, a solution freezes at a lower temperature. So the delta TF is the freezing point depression, right? So I think what your book is trying to say here is that we're just going to use the absolute value for the deltas here. So if there's always some molecules, according to the Boltzmann distribution, that are able to achieve enough energy to break that surface and get loose into the gas phase, right? There's always some molecules going into causing vapor above your water. Like if you've got an open pan of water, there are a few molecules coming off of it, even if your temperature is nowhere near boiling, right? But then when you reach what we call the normal boiling point, look at this curve as it goes up, right? Now this is in kPa's here. So even though there's always a bit coming off, so when we get So when we get up to this spot, and this is in Kelvin, so this is 393 K or 100 C, right? So right there when we get to 100 C, what's happened is, and if you could see this part right here, that's when we get to our, let's say, 101 kPa. Well, that's important because that's the atmospheric pressure, right? That's why at 1 atmosphere or 101 kPa, the boiling point for water is 100 C or 393 K. It's because that's where it reaches that atmospheric pressure. The vapor pressure of water suddenly reaches the overall pressure, and so all then of your H2O is going to go try to get into that gas phase. So boiling point elevation and freezing point depression, they're both a direct result of that vapor pressure lowering. So when the boiling occurs, right, the vapor pressure is equal to the atmosphere. That's when you get that all those bubbles coming in, because suddenly all the water molecules can reach atmospheric vapor pressure. And the vapor pressure is, the amount of vapor pressure then is directly proportional to temperature. Now, the presence of solute in there will lower the overall vapor pressure, right? And now a higher temperature will be required for that overall material to reach that equal to atmospheric pressure, because it's interfered with at that surface. And the boiling point has therefore increased. Now we will have so we'll have some math here with this. So this K is a constant. We're going to call it a constant based on the material that you're looking at. So each different thing, like water has a Kb and a Kf here. So it's a constant, boiling point elevation constant or freezing point depression constant, based on the material itself. And then please don't be confused by this lowercase m. This is one of those symbology things that chemistry is, let's say, less than perfectly clear the way we do this. So what I mean here is this Kb is a constant. I'm going to show you a table in a second that's going to have some of these on it. So we'll look this guy up, right? So we've got a value for K sub B, right? And then this lowercase m in this case means the molality of the solute in the kilograms of solvent, right? So moles of solute per kilogram of solvent, molality here. So this is a molality, and this is a constant to give you how many degrees the boiling point will be elevated, or similarly a different constant, and it will be usually a very different value. But molality still works, but it's a freezing point depression. Boiling point elevation, freezing point depression. And we're going to look these up on a table. It's coming on the next slide here. Like this. So we'll look them up. So if we look at water here, so the normal boiling point at 1 atmosphere here is 100 C, right? But it has this Kb that says degrees C per mole. So every mole per kilogram solute that we have dissolved, that temperature, that boiling point temperature is going to go from 100 up by 0.512 degrees C. Similarly, the Kf is 1.86 C per mole. So for every 1 mole per kilogram of solvent, of stuff, it doesn't matter what stuff, we have dissolved in our water, our freezing point goes down by 1.86 C. And you see that these values can be drastically different, right? Depending on what solvent we're using. Water versus acetic acid, hydrogen acetic acid versus benzene versus chloroform versus nitrobenzene. All of these would have different values, and we can use them. We're trying to use this in some research right now to determine some dye molecules and what dye molecules we're dealing with. We're using this to try to determine their molar mass, which is similar to something we're going to do in a lab with your general chemistry lab. And some applications, a place that you may have seen this in action, right? We don't have it so much down here in Georgia, but if you do get ice forming on a place like, say, where you're walking, you can put a salt down. Sodium chloride will work. Calcium chloride works even better. But you can put this down, right, and it dissolves in the H2O, and that makes the H2O, well, it lowers the freezing point of that water so that the salt water freezes at a lower temperature. So if our ice out here is at 0 or negative 0.5 C, if we put enough salt on it, it'll decrease its freezing point so that it's no longer a solid H2O. All right, and so the way we're going to use this in lab is like determining molar mass from these colligative properties. So we're going to look at a freezing point. We're going to say, well, we can determine a freezing point. We could also do this with osmotic pressure, but we're going to do a freezing point. We're going to say, well, we can tell what the freezing point of a material is with nothing in it, right? And then we can look up its K value on a table, and we can dissolve some stuff in it. The next one here, and so what we can do is we can add a known mass, so we know how much mass we dissolved, and then we can see what happens to its freezing point. Well, now we've got a delta T. We can look up the K value. Well, if we've got a delta T and a K, we can solve for Molal, right? So now I know how many moles per kilogram of solvent. I can determine how many kilograms of solvent I use, right? So now I've got moles. So if I know the moles here, so I can use Molal to solve for the number of moles, right? Well, I also know how many grams I have. So if I have number of grams divided by number of moles, well, now if that was 1 mole, you would tell me number of grams per 1 mole is the molar mass of that compound. So number of grams per number of moles, and then just reduce it down to 1 mole. That's your molar mass of the compound. You can use that. We'll do this in a lab to determine a molar mass. All right, and so we'll have one more lecture, I believe, in this unit before we get ready for our first exam. So at this point, I think we've already done almost all of chapter 11. So just go in there and make sure now that you've got all of 9. I almost cut that off. 9 was our gases. 10 was our condensed phase, and now so gases and then non-gases, and now solutions. And we may not talk very much about colloids, but definitely colligative properties and solubility. All these things. Do read the colloids in case there's anything in there. We'll see what's in there when I record that one next. So make sure that you're caught up now, 9, 10, and 11, but then also any of those older chapters like enthalpy or solutions, chapter 5, that was, I believe, that you need to go back and review to make sure you've got all that stuff too. And let's get ready for the first exam. See you in class.